Paul Bailey, and today I'm going to talk about a universal quantum logic gate called the Deutsch gate and how we propose to create one using gallium arsenide and indium arsenide quantum dots. Before I begin, here's my email, so if you have any questions after listening to this, feel free to email me and I'd be happy to answer them. So first I'm going to talk about what it means for a quantum logic gate to be universal. Then I'm going to talk about the Deutsch gate. And then I'll go into these quantum dots and how they are used for quantum logic gates. And then I'll show you the Deutsch gate circuitry. So first things first, what does it mean for a gate or a set of gates to be universal? So most quantum computing is done with a universal set of gates. That includes something like the C0 gate and Hadamard gate. And so let's say our universal set, for example, was made up of 3 gates called 1, 2, and 3, and they're all 2-qubit gates. What it means for that set to be a universal set means that you can take any target gate, so any gate that you want to create or any quantum computational task, and you can create that gate or complete that task using some configuration of those gates from your universal set. What we're trying to do is create the Deutsch gate, represented here with its angular dependence, which is a single universal gate. So say we wanted that same target gate as is created here, maybe the Deutsch gate, you can create that gate with this configuration. And so we already have some universal sets that work for quantum computing, so why even bother with the Deutsch gate? Well, one thing is that the Deutsch gate is a single gate, and so you only have to worry about how accurate the one Deutsch gate is. Whereas in a universal set, you have to worry about how accurate each one of these gates is. So that simplifies things a little bit. Also, another thing is Ying et al. Found that to create the 3-qubit Toffoli gate, you need at least 5 2-qubit gates, which is what the most universal sets are made up of that we are actually used today. Whereas the Deutsch gate, you just set your angle to pi halves and you have the Toffoli gate. So since we're not restrained to just 2-qubit gates with the Deutsch gate, it may be easier to create higher qubit gates. So the Deutsch gate may be better for particular things than the current universal sets that we have. So that's the motivation behind all of this. So what does the Deutsch gate actually do? Well, the Deutsch gate has 2 control qubits, A and B here, and so when they are in some particular state, we call it 1, then we'll actually trigger a transition. And so what happens in that transition is that the control qubits each pick up a phase shift, while this target qubit undergoes this transition, which is like a phase shift and a rotation mixed. You can see that it has just kind of a phase shift on a part and then you invert it as well. And this is the whole transition represented this way. And the Deutsch gate has never been experimentally realized, and there's only one other proposal that we know of, at least, that uses Rydberg blockade of neutral atoms, and that's Xi, so you can go look into that if you'd like. The primary difficulty is actually this angular dependence, and so you set the Deutsch gate at a different angle and it undergoes a different transition So it's almost like uncountably many gates in one. And so how do we actually want to go about creating this gate? Well, we want to use these gallium arsenide, indium arsenide quantum dots. And these have been used or have been proposed to be used for a few different things, like a C0 gate, a Bell state analyzer. But basically what happens is the electron inside the quantum dot will be in some superposition of spin up or spin down, while an incoming photon will be in a superposition of right-handed or left-handed light. And so depending on which states you have, you get different transitions. So looking at this top row, if we send in left-handed light and we set up our quantum dot to be in the spin-up state, then our photon is actually going to reflect and change its polarization. Whereas if we send down right-handed light with a spin-up state, we're going to transmit through the quantum dot and pick up a phase shift. And so those are the two transitions that can happen. You either reflect or you transmit. And in any of these cases, actually, the electron state stays the same. You also get the opposite transition if you come from below instead of above. So we see that same left and up pair actually just transmits through the quantum dot this time. And so these are all the transitions together. And what this actually does is entangles the electron spin with the polarization of the photon. And that'll be more evident when I show you this example, which is a C0 gate that was proposed by the Baumeister group. And so the C0 gate just has a target qubit which inverts when the control qubit is in some particular state, and it stays the same otherwise. And so the Baumeister group used these quantum dots, or proposed to use these quantum dots, to create a C0 gate. And so again, they had an arbitrary superposition of right and left-handed light for the photon, and they had a superposition of spin up and spin down for the electron spin inside the quantum dot. And so the photon comes in, is split by a circularly polarized beam splitter, right polarized light transmitting, left polarized light reflecting, and then picking up a phase shift here. So that's the state we have. And then the photon interacts with the quantum dot, and we get this entangled state as the output, and it just follows those rules that I showed in the previous slide. And each of these terms with the minus signs are actually coming from the bottom of the quantum dot, and so they will each pick up a phase shift. And then we're left with this output state. And so you'll notice that if the electron was spin up, we got the same photon state that we put in. And if the electron state is spin down, then we invert our photon state. So the control qubit here is the electron spin, and the target qubit is the photon polarization. And this gives us a C0 gate. So what we did is, through similar methods, found how to create the Deutsch gate. And it's pretty complicated, so I'm not going to go through it with much detail at all, but what it's made up of is phase shifts represented by the red boxes, circularly polarized beam splitters, linear polarized beam splitters, these mirrors which just switch the polarization of the light, and then how we introduce the angular dependence of the Deutsch gate is actually through half wave plates. So you just set these half wave plates to whatever angle you want, and then we have these quarter wave plates which are at set angles. And so we start with the same photon state, and both of our electron spin states are just a superposition of spin up and spin down. And this is our output state. What you'll notice is everything aside from the box term, you just get the original photon state out. And only when both spins are spin up will you actually have the Deutsch gate transition. And so this is the Deutsch gate. And so a question you might have is, how feasible is this? And so to look into that, I'm going to show you actually how we can create the Toffoli gate as well. So if we just take a subset of this schematic, this actually turns out to give us the Toffoli gate, which is just a control not gate. So if we have two control qubits, then they both have to be in a particular state 1 to invert the target qubit, and the target qubit stays the same otherwise. And so following the work of Rarity et al., we can actually find what the fidelity of this gate should be based on certain operating parameters of the quantum dots. So the x-axis is the normalized side leakage, so how well does your electron stay in the state you want to be in. And then the y-axis is the normalized coupling strength. And so we see that if we get a small side leakage and a bigger coupling strength, we can get above 93% fidelity. And people have actually been able to operate these quantum dots within this range that would give you 93% fidelity for this Toffoli gate. And so we haven't worked out what the fidelity of the Deutsch gate is yet, but it seems like it should be pretty high based on the Toffoli gate that we have. So in conclusion, we found that you could create a Deutsch gate with gallium arsenide and arsenide quantum dots alongside just some common linear optical elements. And we also saw, and this isn't something we figured out, a lot of people have been doing this, but these quantum dots are useful for creating quantum logic gates and doing other quantum computational tasks. Some interesting questions are, what are the Deutsch gates actually more useful for? We saw that they can implement the Toffoli gate easier, but we're sure that's not the only thing they might do a little better than our current universal sets that are in use. And we also want to see how else we can realize the Deutsch gate. So there's only one other proposal that I mentioned earlier, but I'm sure there are other ways that we could do this. All right, thank you so much.